In this video, I'd like to talk about PBr3 and SOCl2 reacting with alcohols. And these are typical SN2 type reactions, so it's worth covering in this unit. And it leads us to another kind of nucleophilic substitution, which is very, very rare, but still worth talking about, that being SNI, or substitution nucleophilic internal. So we'll talk a little bit about that when we get to the SOCl2. Let's begin by considering a very simple secondary alcohol like this. Very simple. And we react this with PBr3. This is a pretty common reagent. This is old chemistry. And phosphorus is very oxophilic. So, of course, the oxygen attacks it. And I'm not actually going to show every proton shuttling step. That really gets very, very steppy. And this video is going to be very long if I start showing each and every proton step. So I will skip that and simply stick with the main steps. And we get this. And the bromide comes in and performs a backside attack. This gets displaced, and we get our product, which proceeds with inversion. And we get this. Actually, we get this. We can show the proton at this stage. So that's basically the mechanism with an alcohol reacting with PBr3. And what you get is you get the bromine instead of the alcohol, and this chemistry proceeds with an inversion of the stereocenter. So this is PBr3. Now let's talk about SOCl2. And I'm going to start with the simple mechanism, which probably isn't entirely correct, but it's what very often gets taught at this level, at the sort of undergraduate level. And again, I won't show each and every proton step because then it really gets very lengthy, and I want to try to show all of the carbonyl steps. I think it's a little bit more important. So this is extremely electrophilic, obviously, and the alcohol comes in, attacks it, and this happens. And what we get, of course, is this. And typically this is the reaction that that's a pretty wild arrow. Typically this is the reaction that you'll encounter at the undergraduate level. And it simply does this, such that this step is completely irreversible because now we lose SO2 as a gas. This proceeds with inversion, and you get SO2, which sort of leaves up the chimney, plus our HCl, right? Now, this probably actually doesn't happen. This is something that usually you encounter at the undergraduate level, this mechanism, because it's similar to the mechanism with PBr3. And the objective really is to teach students about how carbonyl chemistry works, or in this case, sulfonyl chemistry, how it works. But this mechanism might actually be a little bit more complicated than this. And so let's talk a little bit about it. And it's a very rich subject because there's basically three mechanisms we can talk about. So the first one is SNI. And we will put retention in brackets. So let's talk about SNI. So let's imagine, once again, that we have our alcohol. And we have our thionyl chloride. First step, of course, is this. Okay, next, the SO double bond is reformed, displacing a chloride. And we get this key intermediate. And the SNI mechanism is very interesting. It's actually this. And what you get is this reforms like this, and this returns to the chloronium to neutralize the charge. And so what you end up getting here is retention. You get retention. You get your chloride plus, of course, the SO2 plus HCl. And here's your chloride with retention. And you can see that the product here and the starting material here, they have the same enantiofacial profile. So the chloride, the chlorine, and the alcohol are on the same face of the molecule. So that's SNI. And this is sort of an interesting step here. It's very rare. I don't think you see this very often in organic. And it's probably not entirely clear whether this is entirely concerted or whether this sort of leaves as a semi-dissociated ion pair. Obviously, if it left completely as an ion pair, you would get racemization. And in this case, you don't. You actually see retention. So it's a very interesting mechanism. The second is SN2. With pyridine. Now, if you add pyridine to the reaction mixture, you get some different chemistry. So let's talk about what happens, but let's start at our key intermediate. So this is our key intermediate here. Now, it's a kinetic question here. So here's pyridine. And obviously, this is going to come down to kinetics. This SNI can happen, obviously, but if the pyridine is present in sufficient concentration and attacks more quickly, and this should be a pretty fast attack, then it sort of disarms this moiety here. We can say it sort of disarms it from doing that SNI that we previously talked about. So here's the mechanism. This goes like this. And we get this. Okay. This comes down, displaces the chloride, and we get this. And finally, our chloride comes in, attacks our delta positive carbon, and this happens right here with this bonding pair returning to the nitrogen as a kind of nucleophilic catalysis. And we lose SO2, so of course this step is irreversible, and you get inversion. We have inverted the center. So you get this. And then we can say plus pyridine, right? The pyridine actually could be catalytic in this case, provided that it's present in sufficient quantities such that this attack here happens more quickly than the SNI happens, right? So pyridine, this is what pyridine does. Now there's another case here which is actually maybe even more interesting. This is SN2, and we can say dioxane, and we can say retention, but it's actually a double inversion because SN2 doesn't happen with retention. It always happens with inversion. So if you get retention, you're either dealing with something special like SNI, or you're actually getting what you're actually seeing is a double inversion. So let's go back to our key intermediate that I drew above, which is this one here. This guy right here. And let's say we have dioxane in the mixture. Well, dioxane actually comes in here and displaces this guy. And what you get is, you get this with inversion. plus, of course, this guy here, which really very quickly collapses to this, right? And so we can say this. Okay, and last step, of course, is this. This guy comes in, the chloride comes in and returns the electron pair to the oxygen or the oxonium there. And what you get is this. Now this is actually retention. The chlorine is on the same side of the alcohol, but you can see that the retention went through 2 inversions. So this is actually a double inversion. So some really interesting chemistry with PBr3 and SOCl2, and it highlights both SN2 and that rare mechanism SNI.